So this long, colorful strand is the messenger RNA. That's what is carrying the information that will be turned into the protein. So here now, the small subunit is coming together. These are accessory proteins that help get the process started. So it's come together around the start site. Now, here comes the large subunit, fastens on. And now what's going to happen is the whole machine will work its way down that messenger RNA strand. These accessory proteins go off. So the first step is elongation, and what's coming in here is a transfer RNA. It's carrying at this end an amino acid, and up here in the peptidyl transferase site, the amino acid here, which is a piece of a protein, and the one here on the start codon will form a peptide bond. So that's the first link being formed in this chain. This accessory protein, elongation factor, comes in to help translocate the whole machine, to help it move, and it does move. There's considerable molecular motion here along the messenger RNA strand. Remember, the peptide, the protein itself is forming up here at this end of these transfer RNAs. Now that one goes out. This one will come out of this site, because the whole machine's going to move, and another transfer RNA will come in, carrying up here an amino acid. Go form a bond there. See, that one exits from the exit site. Now we'll speed this up to something more like real time. Actually, it's moving much, much faster than this. So it's reading the messenger RNA strand, and out of a special channel in the large subunit comes the baby protein. Here are all these amino acids linked together, and they're starting to fold. Now here's the step I want you to focus on. This protein is still attached to the ribosome by the last transfer RNA. It has to be cut free to go off and perform its job. This protein does that job. It's called release factor. Comes in here, hydrolyzes the ester bond there. There goes the protein off to fold. And then that comes back out, and then the whole machine is recycled by ribosomal recycling factor, which breaks the two halves apart so they can go off to find another messenger RNA strand. If I had to pick a machine to use to illustrate design in the cell, it would be the ribosome, because it's really much more important than any other machine in the cell. But let's focus just on that release factor. It's essential. If you don't have a release factor, that protein that I showed you that was coming out of the channel, it'll stay attached to the ribosome. It won't fold and it won't function. So release factor is an essential component. All right, let's generate our prediction. All living things share a common ancestor. I just showed you in that video how this system works. And by the way, that was in a prokaryote. We have a more complicated system in our eukaryotic cells. Similar in many respects, but different than others. Anyway, we know that we need that release factor for this system to work. That's an essential protein. So all living things share a common ancestor. We know how it works. What would you predict should be the structure of release factors in any cell that you look at if all living things share a common ancestor? And in that common ancestor, there had to be a release factor. All right, so it's got a particular shape. It's inherited by its offspring. They go off and diverge, but it can't change much in its shape to do its job. So what would you expect here? Put those two together, what would you predict? They should be the same. If release factors are essential for any ribosome to function, and all living things share a common ancestor, when we look at different kinds of organisms, that protein should be largely identical. So there's a pretty clear prediction. And this happens all the time in evolutionary biology, where we take the theory of common descent, link it to other things that we know, and then we generate predictions that we can actually go out and check. All right. There is release factor from E. coli. This is the bacteria that normally inhabit your intestine. Pay attention to the shape of this. It's a molecular tool. It has a particular three-dimensional form that you can download from the protein data bank. Who wants to guess the shape of a eukaryotic release factor? Is it going to be the same or different? It's as different as it can be. You cannot superimpose these two proteins. They have completely different folds. They do the same job, but they're as different as a hammer and a saw. Probably a hammer and a saw actually have more commonalities than these two. When this was discovered, it shocked people. And you can go back and look, when this crystal structure was solved and compared to the one on the previous slide, people were shocked because what they expected to find was the same protein. They expected it because of the theory of common descent. Well, biochemistry is more, I'm about to tell you in more detail, is a lot more surprising than that. This is a refutation of common descent if you let the data speak for itself. No one expected that these would have totally different folds. They do the same job, but they're not the same protein. So let's go back to our prediction. That's false. Now, someone over here has got to pay. The logic is relentless. If you make a prediction and it goes belly up, something in this bundle over here is responsible for that. And the question is it going to be this or that? And as I told you a moment ago, the practice of most evolutionary biologists is to keep the queen in her throne room. And they say, well, gosh, you know, there must be a way for translation termination mechanisms to evolve that we haven't discovered yet. This happens over and over in evolutionary biology, where common descent is insulated from observational challenge. What you could do is say, you know what, we know a lot about this. That's not true. Because somebody here has got to pay for that failed prediction because of the logic of the principle of continuity.